Hello and welcome. My name is Noah Deere. This is Lesson 16, Double Integrals over Polar Regions for Portland Community College's Math 254 Vector Calculus. And in this lesson we will start with an introduction. We'll talk about some polar regions, what kind of surfaces are best described using polar coordinates, and then we will look at the formula for finding volume under a surface given in polar form, and practice that for a second before we get into formulating where this formula comes from. And so we'll go through the whole proof of why we use the formula that we do. Then we'll look at setting up finding the volumes of different solids that are described via their bounds. And then we'll look at some more complicated polar regions where the radius is actually changing with the angle. We'll look at the initial ones where it's essentially just arc circular shapes on the outside, and then we'll look finally in the last section here on things where we have something like the radius equals 3 minus theta, or something more complicated even. Alright, let's jump in here. Section 16.1, Introduction. Some regions are most easily described using polar coordinates. For example, a disk with radius 2 and rectangular coordinates has the equation x squared plus y squared is less than or equal to 4. We cannot solve for x or y as explicit functions of the other variable. We can write that y equals plus or minus the square root of 4 minus x squared, but this is not a function. On the other hand, in polar coordinates, we can describe the disk of radius 2 as simply as r is less than or equal to 2. We can highlight this even more because there's even more complicated regions that are definitely more easily described using polar coordinates. So to further highlight this, the region in the first quadrant and inside the spiral r is less than or equal to 3 minus theta. If we were to do that in rectangular coordinates, we would need to describe it as the square root of x squared plus y squared is less than or equal to 3 minus the tangent inverse of y minus x if you wanted to use rectangular coordinates. This region can be seen here in figure 16.1.1. Go ahead and pull that up in the graph. We're going to get a couple of views of this. Where is this? Alright, so here we can see that region. This outside curve is the line r equals 3 minus theta, and we're looking at the region between that and when r is 0 in the first quadrant only. And we're actually looking at finding the volume under this surface here. So we're looking at trying to find the volume of this solid. This is like the last problem we'll do in this. So this is kind of our end goal for the day, is to be able to do something this cool, this interesting of a shape. So let's go back here real quick. So here we're seeing that the surface is given by f of x comma y equals x plus y plus 1 over the region in the first quadrant, and inside the spiral r is less than or equal to 3 minus theta. It's definitely easiest to find this volume in polar coordinates. Alright, moving on, section 16.2, setting up a double integral using polar coordinates. So to find volumes using polar coordinates, we will use the double integral, the integral from alpha to beta of the integral from r1 to r2 of f of r cosine of theta, comma r sine of theta, times r dr d theta. Okay, so, and we really kind of say it that way, like it almost becomes like a pirate joke, like r dr d theta. So r1, or r naught and r sub, I have labeled these differently in two different spots. Let's make this here r sub 0, and this r sub f. So r naught and r sub f are bounds on the radius of the region we are integrating over, and alpha and beta are bounds on the angle theta over which we are integrating. Note the extra r in the formula before the dr d theta. So this is really key here. Don't forget to throw that on. So let's do this in an example before we prove that this will give the volume that we're looking for. So this definitely does give the volume we're looking for, but let's just practice it before looking at knowing that this is the right formula to use. So example 16.2.1, evaluate the double integral over the domain D of x y squared d capital A, where D is the region enclosed in the unit circle, and to the right of the y-axis using polar coordinates. So here we can see the region that we are trying to integrate over. So we have essentially a half circle that's to the right of the y-axis that has a radius of 1. So the angle that we are integrating over is from negative pi over 2 to positive pi over 2, and the radiuses that we're looking at are from a radius of 0 to a radius of 1. So we'll start by setting that up. We now want, so our double integral over our domain of xy squared dA. This is going to equal, let's scroll back up so we can see this formula that I'm using here. So the integral over the angle, so the angles, like we said, we have a negative pi over 2 to positive pi over 2. And then our radiuses that we're integrating over are from 0 to 1. And then what we want to do is we want to do f of r cosine of theta, r sine of theta. So in for x, we put in r cosine of theta. And in for y, we put in r sine of theta. So here in this equation, since x is here, y squared here, we're going to put r cosine of theta. In for the x, we're going to put in r sine of theta. Quantity squared. So we put r sine of theta in for y. And then the dA becomes r dr d theta. Okay, and again, we'll prove that all of that needs to be there here in the coming pages, but for now, let's just work through this problem. So now we've just plugged everything into the formula. And let's start by simplifying everything. Negative pi over 2 to pi over 2. Integral from 0 to 1 of, so we've got now 1, 2, 3, 4 r's, so r to the 4th cosine of theta sine squared of theta. This is nice. I can see right away that this is going to be a u substitution. If u is sine, then du is cosine. But that'll be in our second integration. Okay, so we can integrate with respect to r first. Since this is a product here, we can break this up into two completely separate integrals. So we can actually write this as the integral from negative pi over 2 to pi over 2 of r to the 4th dr times the integral from 0 to 1 of cosine of theta times sine squared of theta. And I'm racking my brain to see if we've actually done this in the past, because it's definitely allowed. And it's because the inner integral is with respect to r only, so cosine of theta sine squared of theta is really thought of as a constant as far as the inner integral is going. So that can really be pulled. Oh, I totally wrote this in the wrong order. It works if you do it right. Hold on, let's reorganize this. So this should be my angle stuff gets pulled out of the... There we go. So the angle stuff gets pulled out as a constant in regard to that first integral. And then, oops, that multiplication sign in there. We can do this integral separate. So here we go. All right, so for this, I'm going to have u equal sine of theta. So du equals cosine of theta d theta. And so we get that this is the integral. Now negative pi over 2 in for sine is negative 1. And pi over 2 in for sine of theta is 1. So we're changing our bounds of integration so that we're now having u value bounds, because we're now going to switch everything to u's. So cosine of theta du will, or d theta will become my du. Sine of theta squared is u squared. So this is u squared du times, over here I'm going to go ahead and take this integral, and so we get 1/5 r to the 5th evaluated from 0 to 1. And now here I can take the antiderivative, get 1/3 u cubed evaluated from -1 to 1 times, here this will simplify down to 1/5. So we get that this equals 1/15 times 1 plus 1. When I put in a 1, I get a 1. When I put in a -1, we'll get minus -1 is 1. So 2/15 is the volume under this solid. Let's take a look at that picture one more time and see that it's this. We actually could have used some symmetry and done the integral from 0 to pi over 2 for our angle and then multiplied the whole thing by 2 just as well. Either way is totally fine. So kind of a cool little shape there, but we're looking for the volume of that solid. Alright, let's go ahead and flip back. And let's give you guys an exercise. Go ahead and give exercise 16.2.1 a shot. Evaluate the double integral of 1 minus x squared minus y squared d capital A over the domain D, where D is the region inside the unit circle. Go ahead and get that set up. You can look at the GeoGebra graphic if you'd like to as you think about it, and I will work through the solution with you in just a few moments. And we're back. So looking at our double integral over the domain D of 1 minus x squared minus y squared d capital A, this equals the integral from 0 to 2 pi of the integral from 0 to 1 of 1 minus r squared cosine squared of theta minus r squared sine squared of theta, close parentheses, times r dr d theta. And this is because I plugged in an r cosine of theta for x, which squared the r and the cosine. I plugged in an r sine of theta for y to get an r squared sine squared of theta. And we're doing the regions inside the unit circle, so my radiuses are going from 0 to 1, and my angle's going from 0 to 2 pi. Alright, to simplify this down, I can use my Pythagorean identity on cosine squared plus sine squared, which equals 1. So this simplifies down to equal the integral from 0 to 2 pi of the integral from 0 to 1 of parentheses 1 minus r squared, close parentheses, times r dr d theta. Then breaking this up into my theta and my r integrals, I have the integral from 0 to 2 pi of d theta times the integral from 0 to 1 of r minus r cubed dr. Taking the antiderivatives and evaluating, we get that this equals 2 pi times parentheses 1/2 r squared minus 1/4 r to the 4th, close parentheses, evaluated from 0 to 1, equals 2 pi times 1/4 equals pi over 2. And let's just go ahead and pull up this graph real quick. So here we have this cool looking, like, I don't know, cap to something. We're looking for its volume. This is a downward facing paraboloid. So we've cut it off at the xy plane, but we can see, since it's nice and centered over the z-axis, it's nice and simple to reset up the equation from 1 minus x squared minus y squared to polar coordinates of simply 1 minus r squared. And that makes it a lot easier for us to find this volume. And again, we could have done this using symmetry and taking the integral from 0 to pi over 2 for the angles and then multiplying everything by 4, and that would have gotten us there just as well. Okay, now that we've gone through that, let's go ahead and take a look at setting up the formula, where the formula comes from, and we'll go through this in some detail. So suppose we are looking for the volume between the xy plane and a surface z equals f of x comma y in some region D described in polar coordinates with alpha less than or equal to theta less than or equal to beta, and r naught is less than or equal to r is less than or equal to r sub f. Let's build up the double integral in polar coordinates by slicing the region we are finding the volume over every delta theta and every delta r, finding the area a sub I comma j of these slices, multiplying each area by a z value, z sub I comma j equals f of x sub I comma y sub I value, where x sub I, y, whoops, this is x sub I, y sub j is in the slice whose volume we are trying to find, so that the volume v sub I comma j equals z sub I comma j times the area a sub I comma j. So essentially, if we have some slice that's going to look something like this, like a little cut out of a pie or something, then we have the height is some z value. Say we were using this corner here. This is x sub I, y sub j, z sub I comma j. And so you can then take the area of the region that we've cut up, so we have that area, and then we just multiply it by the height, because this is a prism shape, and that will give us the volume. So we need a formula for the area of that little slice, is essentially what's going to need to happen here. So let's take a look. Where are we? We see this in figure 16.3.1 below, where the total volume of the solid can be approximated by adding up the volumes of each of the prisms acquired after slicing up the region we are finding the volume over. So let's take a look at this. Okay, so we take our region, we are going to slice it up every theta. So all of these blue lines are cutting up the region every delta theta. So I've got my delta naught all the way to delta sub n. We've cut it up into n delta slices. So essentially the way that this is kind of being set up is that it's just going from here, this first blue line, to the last blue line. We're not actually doing the entire region in this description right here. We will in the final problem, but we have theta naught, theta sub 1, etc. Then we get to generalize theta sub j minus 1, then theta sub j, and then keep going, and then we'd get theta sub n minus 1, then theta sub n. But we aren't just slicing it up in that direction. We're also going to slice it up in the radius direction. So I have r sub 1 here. R sub naught is just 0 in this case. It's not in every problem. R sub 1 is here. We would keep going. This is r sub I minus 1. This then is r sub I, and then we would keep doing this m times so that we have r sub m as our outer border. We're actually going to look at this using some mid-values of the radiuses that we have, that we've cut it up in terms of. So r sub I bar is the average of r sub I minus 1 and r sub I. So r sub I plus r sub I minus 1 all over 2 is the radius in the middle between r sub I minus 1 and r sub I. Okay, let's get into some of the formality of how we write this. So looking down on this region in the xy plane from above, we can see the slices every delta theta, so that the interval from alpha to beta is cut up into subintervals alpha equals theta naught, comma theta 1, comma theta 1 to theta 2, comma etc. to theta sub j minus 1 to theta sub j. Close that interval, comma dot dot dot, and then final interval theta sub n minus 1 to theta sub n, where n is the number of slices over the theta interval. We also see the slices every delta r, so that the interval from r naught to r sub f is cut up into subintervals, the interval from r naught, comma to r1, and then the interval from r1 to r2, etc., the interval from r sub I minus 1 to r sub I, etc., and finally r sub m minus 1 to r sub m, where m is the number of slices over the r interval. So let's highlight one of these slices to determine the formula for its area. So in figure 16.3.3 below, we can, let's use the word calculate. Definitely not the word us, that's for sure. Okay, Thank you so much for your patience with my little typos here. Getting them all fixed. So the area a sub I sub j is approximately delta theta over 2 r sub I squared minus delta theta over 2 times r sub I minus 1 squared. Let's take a look at that a little bit closer, and then we'll do the simplification here. So here we've got our slice in the theta direction is from theta sub j minus 1 to theta sub j. Our slice in the r direction is from r sub I minus 1 to r sub I. We have a average r sub I value we call r sub I bar, which is equal to r sub I plus r sub I minus 1 over 2. And now our area of this region is going to be, well, we can take the area from 0 to r sub I, so the area of this entire circular sector from theta sub j minus 1 to theta sub j. And to do that, the delta theta over 2 times r sub I squared, that's going to give me the area from 0 to r sub I, this entire sector here. And then we want to take away the area underneath, the area from 0 to r sub I minus 1, so that we're left with just the area in between. And this comes from the fact that if I have some slice of a circle, so here's some delta theta, and this has some length r, the area of this is delta theta over 2r squared. We can remember this actually from the formula for a circle. If I have an entire circle, and we're trying to find the area equals 2 pi over 2r squared. Now we just write pi r squared, but this is half of the total angle all the way around, which is 2 pi. So to get the area of a circle with radius r, the total angle is 2 pi. We cut that in half, get pi, and multiply that by r squared. So this is just scaled down for the area of a sector of a circle. Okay, let's get back to our picture here, and we'll do some simplification. Actually, let's not use the picture. Let's just go back up here. So we've looked at the picture, and we saw that the area of a section between r sub I minus 1 and r sub I, and angle theta sub j minus 1 to theta sub j is going to be delta theta over 2 times r sub I squared minus delta theta over 2 of r sub I minus 1 squared. We're actually going to factor this out a bit, so the delta theta over 2 can come out, and then we have a difference of squares here. I'll fill in an extra step for you. This becomes, we factor out the delta theta over 2 and get r sub I squared minus r sub I minus 1 squared. Then this is a difference of squares that we can factor. So we get delta theta over 2 times r sub I minus r sub I minus 1 times r sub I plus r sub I minus 1. Then the r sub I minus r sub I minus 1, this is delta r. Then I'm moving the 2 underneath the r sub I plus r sub I minus 1, so that this all equals delta theta delta r times r sub I plus r sub I minus 1 over 2. But r sub I plus r sub I minus 1 over 2 is the average between r sub I and r sub I minus 1. So this is my r sub I bar by definition, as we saw in the graphic earlier. So the area of I comma j, or area sub I comma j, equals delta theta delta r times r sub I bar. So the formula delta theta over 2 r sub I squared gives the area of a sector swept out by angle delta theta, and can be remembered as a fraction of the area of a circle, as I was describing before. So we can now finally put all of this together. Now that we have the area of a slice, a sub I comma j is approximately delta theta delta r times r sub I bar. We now have the volume of a prism being simply taking that area and multiplying it by its height, so that the volume sub I comma j is approximately z sub I comma j times capital A sub I comma j. And z sub I comma j is f of x sub I comma y sub I, so this equals f of x sub I comma y sub I times delta theta delta r r sub I bar. by substituting x sub I equals r sub I bar cosine of theta sub j and y sub I equals r sub I bar sine of theta sub j, you can get this volume in terms of just r sub I and theta sub j to be, actually we should put a bar over this, v sub I comma j is approximately f of r sub I bar cosine of theta sub j comma r sub I bar sine of theta sub j times r sub I bar times delta theta times delta r. So we can finally add up all the volumes of all these prisms and let the number of slices m and n over theta and r over the theta and r intervals respectively go to infinity to get our exact volume. So our volume equals, the limit is m and n go to infinity of the sum from j equals 1 to n, of the sum from I equals 1 to m, of f of r sub I bar cosine of theta sub j, comma, r sub I bar sine of theta sub j, close our parentheses here, times r sub I bar times delta r delta theta. And this is the definition of our double integral, which is the integral from alpha to beta of the integral from r naught to r final of f of r cosine of theta, comma, r sine of theta, close parentheses, times r dr d theta. And so we see that that extra r came from the area of the slice needing to be multiplied by the radius up in our previous formula. Where did that go? Right here. It came from when we calculated this a sub I comma j, that we got this average r sub I bar in that calculation. All right. So now that we've gone through the formulation, let's do some practice. Section 16.4, volumes of solids. So example 16.4.1, find the volume of the solid that is enclosed by the hyperboloid negative x squared minus y squared plus z squared equals 1, and the plane z equals 2. Let's take a look at the picture. So here in GeoGebra we have our hyperboloid of two sheets. Where did my mouse go? There we go. And so we have the plane z equals 2. And so we have this region that z equals 2 is cutting off the bottom section of the top, what's that phrase I want to use? So my hyperboloid of two sheets has the sheet on the bottom that is under the xy plane, and we have the sheet that is above the xy plane that is upward facing. So the upward facing one, we've essentially just cut off the bottom little circular region here. So we're going to need to do some extra work to find this, because we need to know where they intersect so that I can understand the radiuses that we're working through. Now here it looks like from the top view that the plane is cutting through the hyperboloid of two sheets at something like 1.7-ish, 1.65, hard to tell. We'll do some math to figure out exactly where that is. But then we can tell that the angles that we're going to be integrating over is from 0 to 2 pi, because we're going all the way around here. So let's do this one step at a time. Get back to my sheet here. So if we look at plugging in z equals 2 into our equation so we can find where they intersect, we get negative x squared minus y squared plus 4 equals 1. So this gives us negative x squared minus y squared equals negative 3. Get rid of the negatives, x squared plus y squared equals 3. So this tells us that r equals the square root of 3. So that radius that we ran into is the square root of 3, which is indeed 1.73. So let's see, where do I want my 1? So if I'm graphing this region from above, I think this one we may not need to do this, but it's never a bad idea. Say 1 and 2, so 2 here, 2 here, negative 2 down here, so 1.73 3, or the square root of 3, is 3/4 of the way to 2 in all directions. So we can draw that the region we're looking at is here. So we want to integrate, oh yeah, that's super fun, over this region. Okay, let's go back here. So in order to do this, we need to get a function. So we want the integral over the domain, which we can work into polar coordinates here in a second. Our z is going to equal, let's move this down actually. So we've got z squared equals 1 plus x squared plus y squared. So z equals the positive square root of 1 plus x squared plus y squared. And we're using the positive square root because we're looking at the top sheet on the hyperboloid of 2 sheets. The negative square root would give us the bottom one. So we want between here and z equals 2. Now z equals 2 is actually our upper bound for this integration, so we really want 2 minus the square root of 1 plus x squared plus y squared. So if we integrated between the xy plane and this square root, we would get the volume between the hyperboloid and the xy plane, which would give us the volume underneath it. So, and we want the volume above it and below the z equals 2 plane. So to do that, we want to do that r f of x comma y equals to the volume under the plane z equals 2, and then subtract the volume from when we do the volume underneath the hyperboloid. And so now we'll go ahead and I'm going to move this one more time. Convert this into polar form. So we have our angles are going from 0 to 2 pi. My radius is going from 0 to the square root of 3. And then we plug in for x and y, we want r cosine of theta, r squared cosine squared of theta, plus r squared sine squared of theta, and dr, oh, don't forget my rdr, so remember we have x squared and y squared in here. When I plug in r cosine of theta for x, it squares both the r and the cosine of theta. When I plug in r sine of theta for y, I get r squared sine squared of theta. We're not plugging in the final r value. Remember, we're integrating from r0 to root 3, and that r varies over this entire integral. So now we can start simplifying this. We have the integral from 0 to 2 pi. You guys want to do this using symmetry? We can see that this is a symmetrical figure. So let's do 4 times the integral from 0 to pi over 2. Should give us the same thing. And then we have the integral from 0 to the square root of 3. We'll have 2r minus r times the square root of 1 plus r squared, dr d theta. Again, I can move my d theta in here, so this is 4 times the integral from 0 to pi over 2 of d theta times the integral from, I'm going to break this up, because here I want to use a u substitution, which I don't want to use for the 2r. So we're going to break this up now into 2 separate integrals. So this, for integral from 0 to pi over 2 d theta, is going to multiply by the integral from 0 to square root of 3 of 2r dr minus the integral from 0 to square root of 3 of r square root of 1 plus r squared dr. And then here I'm going to use u equals 1 plus r squared. So du equals 2r dr. And so the r dr, this implies that r dr equals du over 2. This integral is going to give me 4 times pi over 2. And that's the same thing we would have gotten if we would have done from 0 to 2 pi, just would have given us 2 pi. Here we get r squared evaluated from 0 to the square root of 3 minus, my bounds now are going to be u bounds. If r is 0, I plug that in, I get u as 1. If r is the square root of 3, I plug that in, I square that, I get 3 plus 1 is 4. And then we get a 1/2 du from the RDR, and then we have the square root of u, or u to the 1/2 du. We might be able to squeeze this out just barely with the space provided, so I have 2 pi times, here we get 3 minus, I'm going to say this is now u to the 3/2 1/2 times u to the 3/2 times 2/3, evaluated from 1 to 4. So this is 2 pi times 3 minus, so 4 to the 3/2 equals, the square root of 4 is 2, cubed is 8. So we have then the 2's here cancel, I get 1/3 times 8 minus 1/3 times 1 equals, let's see, 8/3 minus 1/3 is 7/3. 3 minus 7/3 is 9/3 minus 7/3 is 2/3. 2 pi times 2/3 is 4 pi over 3. All right, so the volume between the hyperboloid and the plane z equals 2 should be 4 pi over 3. Let's go ahead and give you guys one to work with here. Now you try exercise 16.4.1. Find the volume of the solid that lies below f of x comma y equals x plus y squared, to the left of the y-axis and between the circles x squared plus y squared equals 1, and the circle x squared plus y squared equals 4. So you're going to have, the radius is not going to be from 0 to some outer radius. Now you're going to have an inner radius other than 0 and an outer radius other than 0. Go ahead and see if you can't hash that out. I've got a little space down here for you to draw the region if you would like to. And I will come back in just a few moments and hash out the solution. Alright, and we're back. So let's get this set up. Our volume is going to equal, well, I drew the picture first, so we've got our region, our angle starts from pi over 2 and goes to 3 pi over 2. Our radiuses go from 1 to 2, because x squared plus y squared equals 1 has a radius of 1, x squared plus y squared equals 4 has a radius of 2. So we're looking for the region inside of here. So angles go from pi over 2 to 3 pi over 2. The radius goes from 1 to 2. So we have the integral from pi over 2 to 3 pi over 2 of the integral from 1 to 2 of r cosine of theta plus r squared sine squared of theta, all in parentheses, times r dr d theta. And that's because my f of x comma y equals x plus y squared. So we plug in r cosine of theta for x and r sine of theta for y to get this expression, and then have the r dr d theta. So I distribute the r, and I get that this whole thing equals integral from pi over 2 to 3 pi over 2 of the integral from 1 to 2 of r squared cosine of theta plus r cubed sine squared of theta dr d theta. Now here I can't factor the r's and the theta functions from each other to break this into two separate integrals. So I'm going to take the integral with respect to r first. So we get this whole thing equals integral from pi over 2 to 3 pi over 2 of 1/3 r cubed cosine of theta plus 1/4 r to the 4th sine squared of theta, all in parentheses evaluated from 1 to 2, and then we'll take d theta. So evaluating from 1 to 2, we get that this whole thing equals integral from pi over 2 to 3 pi over 2 of 8/3 cosine of theta plus 4 sine squared of theta minus 1/3 cosine of theta minus 1/4 sine squared of theta d theta. Combining like terms, we get that this equals the integral from pi over 2 to 3 pi over 2 of 2 cosine of theta plus 15 over 4 sine squared of theta d theta. Now, in this sum, 2 cosine of theta, that I can take the antiderivative of pretty easily, so we get equals 2 sine of theta evaluated from pi over 2 to 3 pi over 2 plus 15 over 4 times the integral from pi over 2 to 3 pi over 2 of 1/2 minus 1/2 cosine of 2 theta d theta, and that's because I'm using a double angle formula to get sine squared of theta equals 1/2 minus 1/2 cosine of 2 theta, because taking the antiderivative of sine squared as it stands is not something that we can really do. So we need to use our trig identity to get through this. So this whole thing equals parentheses -2 minus 2 close parentheses, and that I got from evaluating 2 sine of theta from pi over 2 to 3 pi over 2. Then we get plus 15 over 8 parentheses theta minus 1/2 sine of 2 theta close parentheses evaluated from pi over 2 to 3 pi over 2. I factored out the 1/2 there before I did the antiderivative. I then evaluate from pi over 2 to 3 pi over 2, and we get this whole thing equals -4 plus 15 over 8 times big parentheses, and then little parentheses, 3 pi over 2 minus 0, close little parentheses, minus, open little parentheses, pi over 2 minus 0, close little parentheses, close big parentheses. Simplify this down, and we get equals -4 plus 15 pi over 8. And that should be the volume between the surface f of x comma y equals x plus y squared and the xy plane. We'll note that part of that is a positive volume for when it's above the xy plane, and part of it is a negative volume for when it's below. So now let's go ahead and move on to our last page, our last example, which is really going back to the first page where we looked at a polar region given by r equals 3 minus theta, a spiral. And so we want to look at the volume under the solid, or under the surface f of x comma y equals x plus y plus 1. And we have, things get a little bit more complicated here, but I think we can tackle it just fine. Or at least I'm sure that we have done enough preparation to see, not just from what we've already done with polar coordinates in this lesson, but also where we've had double integrals where, say, we are integrating with respect to y first, and so we have a lower y bound and an upper y bound is actually functions of x, and so we have to plug those in. And so from our previous lesson, we see some of that stuff come back into this example. So section 16.5, polar regions whose radius varies with angle. Example 16.5.1, find the volume under f of x comma y equals x plus y plus 1, and inside the region bounded by the first quadrant and the spiral r equals 3 minus theta. We'll go ahead and look at the graph in a second. Let's just look at drawing that spiral in the first quadrant. So if theta is 0, then, so we have r equals 3 minus theta. If theta is 0, we have a radius of 3. If theta is pi over 2, then we have 3 minus pi over 2. Pi is about 3.14 over 2 is about 1.57, so this is about 3 minus 1.57, which is approximately 1.43. And let's get at least one more point in here. So this is 1.4. Let's put an exact value. 3 minus pi over 2. If we do pi over 4, pi over 4 is half of pi over 2, so that's about 0.75. 0.785. And so that's about 2.215. So we do a radius of 2.2 out here. So a radius of 2 be right in here. 2.2 is going to be about there. Alright, so that should hopefully be enough to get us going. So we're looking at this region here, r equals 3 minus theta. And so if, let's go ahead and look at the graph one more time. I'm proud of this graph. It took me a while to get it all set up. So, where'd my mouse go? So we're again looking at this region here and the volume under this solid. So we're going to integrate from theta is 0 to pi over 2, and from r equals 0 to r equals 3 minus theta is how we want to set this up. So the volume is going to equal the integral from theta is 0 to pi over 2, and my radiuses are now going from 0 to 3 minus theta. So this is the new thing that we're dealing with. We have our radius is not going from 0 to another constant or from a constant to a constant. It's going to an expression in theta. So this is my upper bound on r. And so my function here, we plug in r cosine of theta and r sine of theta for x and y. So we get r cosine of theta plus r sine of theta plus 1 times r, and then dr d theta. This equals the integral from 0 to pi over 2 of the integral from 0 to 3 minus theta, r squared cosine of theta plus r squared sine of theta plus r dr d theta. Again, we can't factor out my functions of r, so we are going to do this all together. We have the integral from 0 to pi over 2 of 1/3 r cubed cosine of theta plus 1/3 r cubed sine of theta. I'm already seeing it by parts in my future. 1/2 r squared, and all of this needs to be evaluated from 0 to 3 minus theta d theta. This equals the integral then. So when we plug in the 0 for r, those will all go away. So I just need to plug in the 3 minus theta here. 0 to pi over 2 of, I'm going to have 3 separate integrals. I'm going to break the, alright, I'll do this in steps for you. We have 3 minus theta cubed cosine of theta plus 1/3 3 minus theta cubed sine of theta plus 1/2 times 3 minus theta squared. When I plug in zeros, those all go away, so this is d theta now. Get this stuff out of the way. Okay. Let's break this up in the following manner. Let's take out a 1/3 integral from 0 to pi over 2 of 3 minus theta cubed times cosine of theta plus sine of theta. I haven't actually moved forward on this, but I think this is going to be a nice way. D theta and then plus 1/2 integral from 0 to pi over 2 of theta minus 3 squared d theta. I'm switching the order here. The squared allows me to switch theta minus 3 and 3 minus theta because the difference will be the same but positive or negative, and when we square it, that will cancel it. This will just make it a little bit easier to take the antiderivative here. So this second integral is definitely the easier of the two. This first one is screaming by parts to me. If I take the derivative of this first bit 3 times, it will go away. This is by parts 3 times. So let's just go nice and slow, pause the video as necessary to hash through this whole thing. So this equals, alright, so I want u to equal 3 minus theta cubed. I don't want to put this here. I want to move. Over here so that I have a little bit of room. So u equals 3 minus theta cubed. Still not enough room. dv equals cosine of theta plus sine of theta d theta. So du equals 3 times 3 minus theta squared. V equals sine of theta minus cosine of theta. Oh, and this is times a negative 1 over here, so negative 3. Alright. So, 1/3 bracket uv is 3 minus theta cubed times sine of theta minus cosine of theta. And this is all evaluated from 0 to pi over 2 minus the integral from v du so minus a negative 3 du 3 minus theta squared and sine of theta minus cosine of theta in here d theta plus this bit's not so bad. So let's work that out over here real quick. 1/2 times the integral from 0 to pi over 2 of theta minus 3 squared d theta. This equals 1/2 times 1/3 theta minus 3 cubed evaluated from 0 to pi over 2. And this equals 1/6 times pi over 2 minus 3 cubed minus 0 minus 3 is negative 3 cubed is negative 27, so plus 27. Not the simplest of expressions, that's okay, it is what it is, equals, or not equals, plus 1/6. Actually, you know what I'm going to do? I'm going to say let k equal this, so I'm going to say plus k, we'll tack it on at the very end, just to save ourselves a little bit of space, yeah? So this equals 1/3. 3 minus pi over 2 cubed. Sine of pi over 2 is 1, minus 0 is 1, minus, plug in 0, we get 3 cubed is 27, times sine of 0 is 0, minus cosine of 0 is 1, is negative 1, plus 3 times. And then we get to do by parts again. So here we have u equals 3 minus theta squared now. And so it's 1 power lower than we saw before. So we're moving in the right direction. dv is sine of theta minus cosine of theta, d theta. So du equals negative 2, 3 minus theta, and v equals negative cosine of theta minus sine of theta. And so we do u times v is negative 3 minus theta squared times cosine of theta plus sine of theta. And we want to take all of this and evaluate it from 0 to pi over 2. And we do minus v comes a plus when I factor out the negative. du, get another now, plug that negative in as, so from 0 to pi over 2, we've got like a bunch of negatives here. I've got these two negatives and this negative here, and then another negative, but I'm going to put it into the 3 minus theta. You know what, I don't want to confuse things. We have minus, and then this negative will cancel with the negative cosine and negative sine. I do have a 2 here, 3 minus theta times cosine of theta plus sine of theta, d theta. And we're starting to get somewhere. Oh, plus k. So this can simplify down now. 3 minus pi over 2 cubed plus 27 plus 3 times negative 3 minus pi over 2 squared. Cosine of pi over 2 is 0, plus sine of pi over 2 is 1. So it'll just be a 1. Then minus negative becomes a plus. 3 squared times cosine of 0 is 1, sine of 0 is 0. So just 9 here. Minus 2 times. Alright, and we get one more by parts. Last one, 3 minus theta is my u. So my du equals negative 1. And my dv equals cosine of theta plus sine of theta, d theta. So v equals sine of theta minus cosine of theta. So we do u times v this is all evaluated from 0 to pi over 2, minus v du, oh, du is d theta, negative d theta. That negative will cancel, we'll get a plus. The integral from 0 to pi over 2 of sine of theta minus cosine of theta. I need to move this now. So we've got, what was I? Sine of theta minus sine of theta d theta. And then we get to close the bracket and the parentheses and the bracket and then put plus k. Equals 1/3 times 3 minus pi over 2 cubed plus 27 plus 3 open parentheses. So we've got negative 3 minus pi over 2 squared plus 9 minus 2 bracket 3, it's hard to read, 3 minus pi over 2, sine of pi over 2 is 1, minus cosine of pi over 2 is 0, so that's just a 1, minus 3, when I plug in a 0, sine of 0 is 0, cosine of 0 is 1, so it makes a negative 1, comes a plus 3, plus, finally, negative cosine of theta, and then minus sine of theta, evaluated from 0 to pi over 2, close brackets, close parentheses, close brackets, plus k, we're just about there. Equals 1/3 bracket, parentheses, 3 minus pi over 2 cubed plus 27 plus 3, open parentheses, let's write this as 9 minus 3 minus pi over 2 quantity squared minus 2 bracket 3 minus, actually we can now write this as 6 minus pi over 2 because those parentheses don't matter, 6 minus pi over 2 plus cosine of pi over 2 is 0 minus sine of pi over 2 is negative 1, and then cosine of 0 is 1, so we have minus negative 1 is plus, wait, hold on, okay, I'm messing with my own brain here. Negative cosine of pi over 2 is 0 minus sine of pi over 2 is negative 1, and then we do minus parentheses, just cosine of 0 is 1, but it's negative, so negative 1, sine of 0 is 0, and just one more line to simplify this down a little bit more here. This then cancels, we just get, okay, now we'll do a couple more lines here. Equals 1/3 bracket, parentheses, 3 minus pi over 2, quantity cubed, plus 27, plus 3, parentheses, 9, minus, parentheses, 3 minus pi over 2 squared, minus, the negative 1 plus 1 cancels in here, so this becomes minus 12 plus pi. That allows me to get rid of these inner brackets, close parentheses, bracket, plus close bracket, plus k, equals, I want to distribute this 3 and see if I can't just combine a couple more like terms here real quick. So 1/3 bracket, parentheses, 3 minus pi over 2 cubed plus 27 plus, in here this becomes 9 minus 12 is negative 3 times 3 is minus 9 plus 27 is 18. And then we get a 3 pi. We get a minus 3 parentheses 3 minus pi over 2 quantity squared. Close off this bracket plus 1/6 parentheses. Actually, I'm going to distribute that 1/6 in, so this is 1/6 times pi over 2 minus 3 cubed plus 27 over 6 reduces to 9 over 2. And let's see if we can't do one more quick thing. I'm going to distribute this 1/3 in here, so I get 1/3. I totally want to combine these. We've got room, I think. I've got 1/3 times this, and if I switch this, this becomes a minus. I can pull a negative out here. I'm doing that because now I can do 1/3 times 3 minus pi over 2 cubed minus 1/6 of 3 minus pi over 2 cubed becomes 1/6 times 3 minus pi over 2 cubed. And then we have a 18 over 3 is 6. Actually, I want to do that last. I want to do the 3 minus pi over 2 squared term real quick. So that times 1/3 is minus 3 minus pi over 2 squared. And then we've got the pi term here is plus pi. And then my constant. So then 18 over 3 is 6. Plus 9 halves is 12 plus 9 is 21 halves. All right, that's not a horrible form, but a lot of tedium to get there. I would not blame you for this is not an exam style question. This is, hey, can we work through all of our integrals and our by parts over and over again? There's obviously a lot to this problem, and we can get very complicated things going on. And it would be great if you could have that attention to detail to work through all of these by parts one at a time and get through all of them. The key thing from this lesson is getting this set up and recognizing that the bounds on our radius are from 0 to 3 minus pi, 3 minus theta rather, and to not forget the r before the dr d theta, to plug in r cosine of theta for x, r sine of theta for y, and if you plug it into your calculator, we should be able to confirm that we have the right answer down here, and I'm almost afraid to do so because there were so many steps I very easily could have made a mistake. Let's do it just to find out. I'm super scared right now. 1 second. Actually, I'm going to let you watch my discovery here. Wolfram Alpha. I go to wolframalpha.com. I'm putting in the double integral. Let's see, how do I plug this? Alright, so integral from 0 to pi over 2 of the integral from 0 to 3 minus theta of r squared cosine of theta plus r squared sine of theta plus r dr d theta, 12.0855. And I'm a little scared about that 6 being the constant here. Oh, but in mine we have some foiling to do. So this doesn't quite have the same form. So may still be out of the woods. Let's take a look. I want 1/6. Write this down. 1/6 3 minus pi over 2 cubed minus 3 minus pi over 2 squared plus pi plus 21 over 2. I'm going to bring this back over, and I'm going to open a new Wolfram Alpha window to put this into. And we've got 1 over 6 times 3 minus pi over 2 to the third minus 3 minus pi over 2 to the second plus pi plus 21 over 2. Moment of truth, 12.0855. Oh, I'm crazy stoked. That means I didn't make any mistakes in there. That's kind of amazing. I very much make mistakes all the time. So if you didn't get quite the same thing, just look back, see if you can find any missing negatives. That's going to be our easiest place to make a mistake. But at the same time, we're not going to be giving you some sort of example on it or some sort of problem on a test or anything where it's going to have that many detailed steps for you to get through. Our computers definitely help us work through some of these problems. So even if you've plugged this in here to get this answer, that's pretty good. You've understood how to set up the problem. Oops. And at least get a computer to evaluate it, even if all of this tedium is beyond you. So anyways, that's all we have for you today. Go ahead and work through the homework. Thank you so much for listening, and I will talk to you in the next video. Have a great day.